Okay, so before we decided to proceed any further, okay, by looking at what we have been talking about, this chapter mainly deals with that of acids. So we can safely draw everything that you see here, okay, and then we'll fill in those gaps as we go. You won't have to erase anything, okay, so just look at it that way. And this process is called esterification. And what that means is, and you'll perform this over in the lab probably sometime next week. And it still amazes me to this day how something like butyric acid or butanoic, okay, one's a common name, one's the scientific name, can smell so awful. You mix it with an alcohol and then a strong acid catalyst, sulfuric acid, and it has to be, I want to say, a narrow temperature range, but it does have to get up to a specific temperature, because if it doesn't get warm enough, it's not going to react or break apart the way that it should. If it gets too warm, it'll start to denature and break down. And one way to look at that would be, I think, kind of like sticks of butter. You put that in the microwave, and of course the bonds in between them carbons are just going to start to come apart. So it goes from, we could say, more so of the semi-solid type to breaking down to a liquid. So with that being said, okay, if this was going to be butanoic or butyric acid, how would we change this to an acid now? Okay. Okay. So then we'll put this here for a specific reason. And then, like we said, we react that with an alcohol. And with that, again, and I know I've asked about this color coding, does it make any difference? And I think you had said no, but even in my case, I still think it's very beneficial. So then maybe you're thinking, so why do you ask anyway? If you're going to do what you want, why are we asking? Well, I guess that's probably a good question in itself. Okay, so then I did want to leave this up here. Use the boxes to illustrate this reaction. So what is it that we said last semester and even this semester? We said this common theme. These reactions are all about what? All about the water, whether you're adding it, whether you're subtracting it. In this case, you will be subtracting it because we've got this strong acid catalyst, and we're not too concerned about what the temperature range is. We just know that they're going to react. And with that, we just want to use boxes to illustrate how we're going to take that apart. Okay? And with the color coding, I think we can see what's actually going to happen then. So when we look at this butyric acid, obviously since this is written in green, that's written in purple, this gets stripped off of there. This OH, okay? And then since this is all written in what, maroon or red or whatever color you want to refer that as, and then this hydrogen's in black, that gets stripped off of there. So there's our example of saying this is all about the water. So when you have this acid catalyst and you got your temperature range that this would react, these two come together. So if it's got a box around it, it's no longer there. But notice that bond is still here. We put a box around this OH. So that is going to react with this propanol now. So we're going to link these two together. And then we've got this. Okay. So one of the things we want you to illustrate correctly on how this process works. And I think that's probably why we color code this. And this is why, okay? Because we do want you to be able to know how this process happens next time you see it. So this is what I'm getting at. I'm just going to make this a lot simpler with smaller compounds. Okay, so notice we got a similar type of pathway here. You don't need to write this down. We'll probably do this maybe some other time. Technically, if you wanted to look at it this way, we could say this OH comes off and then this hydrogen. You would still get the same answer. You got that oxygen attached to that double bonded carbon, or this oxygen attached to this carbon with the double bonded oxygen, and you get something very similar to this. But this is not the pathway that this reaction occurs. The OH group actually comes off of the acid part. The hydrogen comes off of the alcohol part. So again, my point is you'd get the same answer, but for the wrong reasons, because sometimes that's possible. It's not saying that you're right, but you're still wrong, or you're wrong, but you're still right. But we want to make sure that this is done accurately. So, and maybe when you do that, maybe just say in alphabetic order terms, acid comes before alcohol, so then that's why that takes the OH and that's just the hydrogen. Maybe, I don't know, whatever, maybe it works for yourself. Just, there's other times we use those types of phrases like, what is it, we're talking about digestion of proteins, those two different types of cells in your stomach. One's parietal cells, one's chief cells. Since there's an A in parietal, that's what actually secretes the acid. And then the chief cells then secrete the pepsinogen. So we've used those types of terms in the past. And then another example we could say is the terms osteoblasts and osteoclasts. Both of them are types of bone cells. And with that, since osteoblasts has a B in it, we would say that's what actually builds a bony matrix. So that way then you know the osteoclasts is what destroys bone tissue and the osteoblasts actually builds it. So you sometimes come across those different types of ways to help maybe make sense of this and keep this straight. And you might be asking yourself, well, why does it make any difference? Well, I think, and I didn't read far enough for what the author had said, but I believe that since we got a carbonyl carbon here, okay, this does not hold on as tightly to this OH group as what this type of bond does with this oxygen. With this carbon, it doesn't hold on to, this holds on more tightly, and then what this one does, it's willing to let it go, and that's just the way that it reacts. That's the best way that I think we can come across that. But what we do want you to do is you don't have these different types of color or markers when you're doing this. You might have with a multicolored pen, but what we want you to do is be able to illustrate this process, okay? Whether it's carboxylate salts, whether it's this process of esterification, and then it'll be just the opposite of hydrolysis. We're actually going backwards. This is another reaction to where you can take an ester, add water to it, and get back the same components that you started with. And we've done that before. I can think of like 3 examples right off the top of my head. Alkenes, you add water, you get alcohols. You can take alcohols, dehydrate them, go back to alkenes. You can take primary alcohols. You can take secondary alcohols and you can oxidize them into ketones. You can take ketones then and reduce them back into secondary alcohol. So we've seen that throughout the course of the year. But this is probably, I want to say, maybe one of the more difficult ones to remember because it's going to be tied into the naming part of it. And when that happens, you need to be able to remember which side is the acid side, which side is the alcohol side. Because you're not going to name this first. You actually name the alcohol portion first. So when we get to that on Thursday or tomorrow, we're going to review this process, then also talk about naming these. So the alcohol portion comes first, I believe. So this is a propyl group, and then this has 4 carbons, so you would call that propyl butanoate. But we're not that far. We're going to save that for tomorrow. So that's all I've got. Maybe you can't think of any questions, or hey, if we don't ask any questions, he'll shut up. Are we good? Left side? Middle, are we good? No? Okay, we'll come back. Right side, are we good? Yeah. We got imaginary students. Just, you gotta have something to laugh about. Okay, we'll catch up to you next time.